So good morning student, welcome to the today's class. So we are in the course Algebra and this is lecture number 18. Okay, yeah, so we saw that in last class we discussed about one special class of groups called Hilbert groups. Okay, and similarly today we will discuss another special class of group, and this special class is called solvable group. Okay, so before that, let us first define few, for example, few definitions. So let G be a group, and and we have a series of subgroups. Say A0. A0 is identity. Identity means consisting of a single element, and which is subgroup of each one, and so on. Okay, so this something say is K, which is equal to the full group G. Okay, so we have a group and then we have some subgroup H0, H1, HK, such that this satisfy this kind of inclusion relation. Okay, so this series, okay, number one. So the above series is called a subnormal series if what happen if Hi is a null subgroup of Hi plus 1, the next one, for all I equal to 0, 1, and then k minus 1. Okay, so H0 is null subgroup of H1, H1 null subgroup of H2. Then it becomes, then this is called a subnormal series. Okay, and then so if this Hi is normal inside G for all I 0, 1, 2, and k minus 1, not only inside the next one, it is normal to the full group. Then the above series is called a normal series. Okay, normal series. Okay, and now the definition. So let G be a group with a subnormal series, say H0, which is identity, and then H1, and then H2, and so on, and say Hk, which is equal to G. Okay, G is called solvable. It's called a solvable group. Solvable group if what happen if there's normal, right? Subnormal means the question is normal. So if this Hi plus 1 mod Hi, so this is another group, right? Quotient group is abelian. If this is abelian for all I, say 0, 1, k minus 1, then this series is called, then the group is called solvable group, and this series is called solvable series. Okay, so what does that mean? That means a group is okay. So then in that case, this in this case, the above series is called a solvable series. Okay, so G is solvable means G has a solvable series. A group is solvable if it has a solvable series. Okay, so this is one definition, and obviously you can ask first question that what are the example of this kind of groups. So you can start with some examples. Okay, so number one, so abelian groups are oh, abelian groups are solvable. Okay, why? Because whenever you have abelian groups, you know that as in if G is abelian, then what happens? Then every uh, so 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 you don't need the full thing. Then you just then you can define a solvable series directly. Then identity, and then this. So this is a solvable series, right? G itself abelian, right? So the question group is G, which is abelian. So abelian groups are always solvable. Okay, and then the question is that we learn another type of class of group last class, right? Nilpotent groups. So what happened to nilpotent groups? So let's see. So nilpotent groups are also solvable. Also solvable. Okay. Why? Because if G is nilpotent, then what happened? You remember? Then we have a upper central series, upper central series, which terminates at G, right? So that is what. So we have that Z0G, which is identity, and then you have first center. Okay, and then the second center, and so on. And then after some time you'll have something zk of G, which is equal to G. This is the meaning of nilpotent group, right? And what is known? The known fact is that Zi plus 1 mod Zi. So this is actually the center of G mod Zi, right? So this was our definition for sorry. So I should say here G. Here also I should write down G. Here also I should write down G. This is the definition of upper central series, right? So you see this Zi plus 1 G. This quotient group is actually the center of another group. So what does that mean? That means the quotient group is this quotient group is thus all the successive quotient are abelian, right? Because this is true for every I, for all I equal to 0 to k minus 1. Because the successive quotients are always center of a group, and center is always abelian, right? So they are abelian. So what does that mean? That means the upper central series itself gives you solvable series. Thus the upper central series is a solvable series for G, and G is solvable. Okay. Yes. So the two important class are already solvable. You know that. So that means solvability is kind of bigger than abelian and nilpotentness, right? The question is that do we have some element in solvable group which is non nilpotent, right? So does this solvable whatever solvable groups or the set of the set of solvable groups has an element which is not nilpotent. So that means other than nilpotent thing, do we have something? The answer is yes. So for example, okay, so for example, so let us discuss this S3, that symmetry group over 3. Now you remember S3 is not nilpotent, as so in S3 what happened, you have Z1, the center of S3 is always identity, right? And hence Z2, S3, everything is identity, right? And so on. So S3 is not nilpotent. Okay, but we will show that S3 is actually solvable. Now why? Because in S3, in S3 you have something called A3, so A3 is sitting inside S3, right? As a rather like the normal subgroup, as a normal subgroup, right? As a normal subgroup. A3 means the alternate group over A3, right? So what does that mean? That means you can start with identity, which is not subgroup over A3, and now if you go modulo A3, you see the S3 mod S3 is also abelian. So this is a solvable series. This series, why? Because if you go successive questions are what? So first one is A3 mod identity, which is isomorphic to A3, right? And second one is what? So S3 mod A3, and you check this isomorphic to Z mod to Z. Now this is also abelian, this cyclic, both are abelian, right? So this is actually a solvable series. So thus this identity A3 S3 is a solvable series in S3, right? And so S3 is solvable, right? So what we show that solvable class is bigger than the nilpotent class, right? Every nilpotent group solvable, but there are solvable groups like S3 which is not nilpotent, right? Now eventually what you can see that you have a you can have a class of groups, okay? So sorry, abelian groups, so abelian groups, and then you have bigger class which is nilpotent group, nilpotent groups, right? Abelian groups are sitting inside nilpotent group, and then you have much bigger class, solvable group, solvable groups, right? And then obviously these all are sitting inside that the groups. So this is all the groups, right? All groups, right? So this is kind of a containment relation between this special kind of group. Obviously inside abelian group you have another group, cyclic group. So I should say that cyclic group, or even inside abelian groups. Okay. Okay. So this is one of understanding the solvable groups. But there is another way of understanding using something called derived series. So let me now discuss what do you mean by that derived series. So or maybe commutator series. So we already discussed commutators and derived subgroups, right? So now let me define it formally again, the series. So for any group G, we define this G0 equal to G, and G1 is the derived subgroup of GG, that is G dash, right? You already know that. Similarly, G2 is a derived subgroup of G1, and so on, right? So and so on. So like G I plus 1, this is the I plus 1 as a derived subgroup, and this is by definition Gi. Okay. So if I define by these, then what happens? Then you will obviously have a chain of subgroups, right? So see, remember this is a different containment. So this is G0 is always bigger than this G1, and then so on, G2, and so on, right? Now question is that whether this kind of chain terminate to identity or not. So whether you have something somewhere after some time identity or not, I don't know. Okay. Maybe I can give an example here, then you will understand the similar example with S3. So suppose you have a S3, G is S3, and then you try to find out what is your G1. So G1 means the commutator subgroup G dash. So what is that? That is S3. But what is S3? So what are the subgroup generated by what are the subgroup generated by the commutators of S3? Now you check, this is nothing but A3. Simple. Now you check it, homework. Okay. And then if you want to do it for second derived subgroup, so these GIs are called ith derived. These are called ith derived subgroup. Sorry, this is I plus 1. Yeah, the GI is called the ith. So GI is called the ith derived subgroup. Okay. So the second derived subgroup is what? This is A3. Okay. Now you check that this is actually A3 is abelian, right? So whenever you abelian thing, then that is we already proved, right? The derived subgroup, a group is abelian if and only derived subgroup is identity. So this is nothing but identity, right? So what does that mean? That means if for like S3 you check that after two stages it terminates to identity. So in general it may not be the case, right? but we already showed that S3 is solvable group. So question is that does it is true that it is actually equivalent to solvability? And the answer is yes. So this is a very important theorem, and this is going to help us in future. Okay, so say group G is solvable if and only if G power n equal to identity, I mean the ideal subgroup, for some n, n, I mean if n equal to 0, this is identity itself. Okay, identity group. Clear? So this is the theorem. So we already know the definition using solvable series, but now we are telling that we can use this by the derived series. So this kind of series is called a derived series. Yeah, so they are called derived series. Derived series, or also sometimes called commutator series. Also commutator series. Okay. So if G is solvable, if only you have a derived series which terminate to identity after some certain stage, finite number stage. Okay. Now, how do you prove this kind of theorem? So, this is if and only condition. So, what does that mean? So, you have you need to prove two ways, right? The proof. So, what we'll do? So, we will first assume that G is solvable, and then we'll check that the derived series terminate. So, let G is solvable, and what and we have a solvable series. So what is solvable series? Yeah, this your kind of identity, and then h1, and then so on. Okay, and some hk. This is your solvable series. Okay. So what does that mean? That is h I plus 1 mod hi is abelian for all I equal to 0, 1, 2 dot dot k minus 1 for every such I, right? So this quotient groups are abelian group. Okay. Now we claim that the derived series are actually satisfying some nice relation related to hi. So how to claim? So this is my claim. So claim that the ith derived subgroup is actually sitting inside this h k minus I. Okay. Now how do we prove? So we prove this claim. By induction. Okay, on I. Now what happens when I equal to 0? So for I equal to 0, what happens? G0 equal to G, and you see that H k minus 0 is nothing but H k, which is nothing but G itself, right? So this is true, right? For I equal to 0, claim is true. So claim is true for I equal to 0. Now we assume that this claim is true for something for some I, and we'll check that for I plus 1. Okay, so now let this G, this is true, true for say I, and now we will check that what happened for I plus 1. Now for I plus 1, what happened? This I plus 1 derived subgroup is by definition Gi, Gi, right? But Gi is a subgroup of Hi plus 1. So this is subgroup of Hk plus 1. Hk minus I and then Hk minus I. Right? So this I plus 1 derived subgroup is subgroup of this. Now question is that can you show this is subgroup of that Ki plus 1 means Ki minus 1. Okay. K of I plus 1. So K minus I plus 1 means K minus I plus minus 1, right? Now how to show that thing? That this is the thing. So now recall that we proved that if this so this is we proved last time in last class in the commutator class that H K minus I mod H K minus I minus 1. So this is abelian, and hence what happened? Hence the derived subgroup H K minus I, derived subgroup of this, actually subgroup of H K minus I. This is the property of the commutator subgroup, right? This you already know, we proved it last class. So what do we assume? We choose this G equal to, we choose G equal to K minus 1 I and H equal to H K minus I minus 1, and then you use the theorem that if H is normal to G and G mod H is abelian, then what happened? Then the G dash is sitting inside H. Remember? So this is the same exactly I am telling that. Write down H equal to G equal to this. So this is the G dash, then this sitting inside this group. Okay. So the property which we proved yesterday, last class, that tells you that Gi plus 1, that is subgroup of H K minus I plus 1. So that means K minus I minus 1, right? So this is the induction part proof. So thus uh, the claim is true for all I, and in particular when you choose that I equal to say K, when I equal to K, then what happens? Then you have Gk, which is subgroup of H K minus K, nothing but H0, and we know that H0 equal to identity. So what does that mean? That means Gk is actually identity. Subgroup of identity group means identity, right? So this part tells you that whenever you solvable group, then the derived series terminates to identity up to certain stage. Okay. Now the conversely, the converse part need to also prove. So now conversely, let us assume that G has a derived series which terminates at identity, at that identity group. That is what, so you have G0, which is G itself, and then G1, so on, and then you have some GK, which becomes identity. Okay. So we need to prove what? We need to prove that that first of all they are normal and the successive are cos. So this is first part is obvious, right? So Gk is identity. So this is identity, and this is normal to Gk minus 1. That is obvious. If you don't have, then I will prove it. Okay. If you don't understand this part, why this is normal? For why this all those things normal? because you see, by definition, G. Okay, so again I need to use that fact that what we proved last time, that you use what is G. Uh, what is GK? So GI plus 1. GI plus 1 is actually derived subgroup of GI and GI, right? So GI plus 1 derived subgroup of GI. And what does that mean? So that means, so this is sitting inside GI, right? Obviously derived subgroup. So what does that mean? That means, so this is GI plus 1 is nothing but derived subgroup of GI, right? So derived subgroup of GI is sitting inside GI. So what does that mean? So this implies that if something in derived subgroup is sitting something, then what happens? Then this becomes the normal subgroup. Remember? So that means GI. So okay, 1 minute. So this is GI is the G. So GI is the G, and GI plus 1 is 1 minute. I should say GI minus 1 here. Okay, 1 GI plus 1 is bigger than that, so GI, yeah, so it's fine. So GI plus 1 is actually not subgroup of GI then, right? Because this is, see, you write down G equal to GI in this case for checking port purpose. And the theorem we proved last time, and then you will see that this is not subgroup. So this is for all I equal to 0, 1, 2, k minus 1. Now why these are this is a solvable series. So to prove this is solvable series, what we need to prove? We need to prove that the question groups are abelian, right? Now what is the question groups that we need to check first? Now let us check it. Uh, so here I will write down my HI. So HI I will write down G K minus I. Okay. Yeah, so HI I will write down GK minus I. I will say that this H I so H0 equal to identity and H1 and so on, and then HK, that will give the full group. Okay, 1 minute. So H, what I am to prove? HK equal to yeah, this is the other way. So this is G. Okay. This is the other way. When I equal to 0, you'll have GK, and GK is the identity. So H0 becomes identity. Yes. When I equal to K, then HK equal to the H0 equal to G. So HK equal to the full group. Yeah. So I write down that this thing. So the normality is okay. I just prove it, but now we need to prove important part that the question group are successive question groups are abelian, right? So Hi plus 1 mod Hi, that need to be abelian. But what is Hi plus 1? So Hi plus 1 is nothing but G. Okay, so this is K. G K minus I minus 1, and here what you have? You had K minus I, right? Now why this is abelian? So this is normal, we already proved it, right? This is normal to this, that already proved, because this one, see, this GKI is the derived subgroup of GK I minus I, comma G K minus I minus 1, right? Yes. And so hence this is null subgroups. Okay. So that is property of commutators. We already proved it. So this commutator subgroup is a null subgroup. So this is null subgroup. Now why this is abelian? Now abelianness will come from the property that again you remember that if g dash is sitting inside H, then H will be normal, and not only that the question group is abelian, right? Now here what you will choose? Here you choose that. So you recall the property. Okay, so recall, although you will forget, recall that if you have a group G such that G dash is sitting inside H, another subgroup, then H will be a null subgroup of G, and G mod H is abelian. Okay, so this is we already proved last class. Now here, um, here you apply this thing with so HI, your HI is now H, and Hi plus 1 is Hi plus 1 equal to G, right? Now you see that Hi plus 1 equal to G. So what is so I need to check that Hi is normal in Hi plus 1. So to show this, what I need to show, I need to show that the derived subgroup of this Hi plus 1, this is inside Hi, that I need to show. But this is obvious, right? What is derived subgroup of Hi plus 1? This is nothing but Hi plus 1 comma Hi plus 1, right? Clear? But Hi plus 1, what is the definition of Hi plus 1? This means this, but the definition of Hi plus 1, this is the, by definition this is yeah, so you see Hi equal to Gk minus I, right? So this is Gk minus I minus 1. Similarly Gk minus I minus 1, and hence this is nothing but Gk minus I, right? So this portion is Gk minus 1, which is actually Hi, right? So this is actually Hi. So what does that mean? That means this is actually same. The direct subgroup is actually same. Say inside this. And then by the property commutators group, that these question groups are all abelian, right? And hence this H0 H1, that becomes a this identity is a solvable series of G. Okay, so G, that means G is solvable, right? So if you just prove that G is solvable, if you only if that derived series terminates as identity for after one intermediate stage, and the smallest k for which this gk is identity is called the solvable length, solvable length of the group G. Okay, solvable length. Clear? So and this the idea of this is going to help us in many cases. For example, if you want to prove that what happened to subgroup of a derived series, subgroup of a solvable group, does every subgroup of a solvable group solvable? So the answer is the properties. You can write down that subgroup of a solvable group is solvable. So whenever you have solvable group, every subgroup is solvable, right? Now to prove this thing, so Now suppose it is given that the proof is also not difficult. So suppose H is subgroup of G is given, okay, and I know that G is solvable, right? So I know that and some G power K equal to identity for some K whatever, okay. So now you see that G, what is G, H subgroup of G means what? For any I, this will be always sitting inside this, right? Clear? Because H is a subgroup of G, so the derived subgroups are always subgroup of the derived subgroup of H, right? And that is obvious because, for example, H1 is nothing but um, derived sub. Okay, so H0 is H, H1 equal to derived subgroup of H, and that will be again subgroup of GG, right? Because every commuters of H, they are commuters of G also, and this is nothing but G1, and so on. Now you use induction. That tells you that for every I this is true, right? So what does that mean? That means H of K is also identity, as G of K is identity. Okay, and hence H is solvable. So subgroup of a solvable is always solvable. Okay. Now similarly, you can ask question group and of image of solvable or not. They are all solvable. So maybe I can write down a general thing. Suppose we have two groups. Say for example, let me write down. So suppose we have two groups, say G and something, say M. Two groups and you have a phi onto map. Okay. So suppose this and you have two groups and phi is a and onto homomorphism. Then what happens if you have onto homomorphism? Then this image of these derived subgroups are actually same for each I. This is for all I. Okay. So how to prove this kind of thing? So this is almost we have already given similar proof last time also. So let me also give here. So here see, remember. So first let me prove that this is true for say I equal to 1. So for I equal to 1, what happened for I equal to 1? You see that so this G1. So G1 is what? G1 is G. So the elements of these are generated by the commutators, right? So now if you choose any commutators, what will be the image of that commutator? So that image will be nothing but that. This is already proved last time, so I am not giving the full proof again. This is the commutator of this, right? But what is this? This is actually commutators inside M, right? So these images are all sitting inside M1. Okay. So what does that mean? That means G1, the first derived subgroup is subgroup of M1, right? And as phi is onto, this is actually equality. Onto we have yeah. So this is phi of G. Oh, sorry, phi of G. We have phi of G1 is actually equal to M1, right? Clear? So now obviously you can do the induction, mathematical induction. Now same proof using induction. Hold up, you have phi of Gi for each I, they are equal to Mi. Okay, now what is the advantage of this thing? So once you know this thing, you can easily prove that homomorphic image will be always of solvable, which is always solvable, because whenever this will end at some some integer k, then phi of that will be equal to m of that also n, right? So thus homomorphic image of a solvable group is also solvable, right? So as if g power k equal to identity, then what happened? Then phi of g power k, that will be nothing but m power k, right? But you know this identity, image of identity is identity, so m power k equal to identity, and m is solvable. That means, okay. So this is also proves that that quotient group. So for quotient group, what do you have? So suppose you have a subgroup of G, null subgroup of G, then you can talk about the natural homomorphism from G mod H, right? So the natural homomorphism G going to GH. So this is onto homomorphism, right? So that tells you that we have onto homomorphism. So if this is solvable, then this is also solvable. So quotient groups of solvable groups are also solvable. Clear? I think this should be now clear. Now you can ask the converse question. What happens if you know that you have a group G and then also a group N such that N, so what if, so my question, now it is given that N is also group G such that N and G mod N is solvable, sorry, they are solvable. This is given. What about G? I mean, I'm asking that if you know the quotient group and the null subgroup both are solvable, can you say that G is solvable or not? And the answer is yes. Yes. Yes, G is solvable. How do you prove that G is solvable? Now proof. So first let me assume. Okay, uh, so so let so let G mod N is solvable of length something, say you write down, say um, n, and n is solvable of length something, say k. Okay, now we know that this canonical homomorphism from G to G mod n, right? This we know. So I don't know, there is a problem. I think my laptop become very hot, so it become problematic now. So you want to, then if you go G of say length n, no? So what does that mean? So this will be equal to G mod n of n, right? But this is, you know, this is solvable of length n. So what does that mean? That means this n derived subgroup is nothing but identity. So this will be identity of G mod n, which is nothing but n, right? Identity of G mod n is 1n, which is nothing but n, right? So what do? You prove that phi of G of n actually subgroup of n, right? This is okay. Uh, Another only phi, I should say phi, because phi of G mod n is sitting inside, uh, this is equal to n, so yeah, what happened, yeah. So phi of G mod n, so this is equal to this, but this is what, this is inside also G, right? So this subgroup is what, this G mod n is actually subgroup inside n, right? But also you know that n is nil parent of what is the class, I assume k. So if you go with this over k, then what happens, then it will be n of k, right? But you know that n of k is identity, so this is identity. What does that mean? That means g n plus k time derived subgroups actually identity, and that means g is solvable. Okay, so maybe this is one nice place to stop here to this lecture. Okay, and we will have the midterm exam, and then after midterm exam we will start something new. Okay, so all the best students for your midterm exam.